All right, so this section, we're going to combine two sections together to talk about exponential functions. Section 4.8 is really about the functions in general, and then 4.9 is about models, which we've already dealt with some of the other things we've talked about this year already. So an exponential function has the form f of x equals b to the x, where b is your base. B is greater than 0, b is not 1. If you have 1 to the x power, it's just going to be 1. That's a straight line, which is pretty boring. So an exponential function has the following characteristics. You have a horizontal asymptote at y equals 0, which is the x-axis. And what that means is that your graph's getting super close to the x-axis, but it's not actually touching it. Your domain is negative infinity to infinity, which would be all real numbers. You can take something to any power and get an answer. But your range is 0 to infinity. If you take a constant to a, well, like let's look at an example here. If I take 2 to the x power. If I take 2 to a positive power, I get a big answer. If I take 2 to a negative power, that's 1 over that number. So that's going to be a decimal. And if I take 2 to the 0 power, I get 1. So there's no way that you can get 0 or anything negative. There is no x-intercept since we get super close to the x-axis, but we don't touch it. But there is a y-intercept at 0, 1. If your b value is greater than 1, like 2 to the x, that's going to give you an increasing function, which is the one on the left. If your b value is something like 1/2, it's less than 1, that's going to give you the graph on the right, which is a decreasing graph. Now, they are going to talk about negative powers and fractional powers, which is very possible for you to have. Like I said earlier, a negative exponent is the same thing as putting it on the bottom of a fraction. A fraction exponent is the same thing as a root. So 9 to the 1/2 power is the same thing as the square root of 9, which is 3. If you stick a negative on it, kind of combining the last two examples, that's going to put your answer on the bottom of a fraction. 1 over the square root of 9, which is 1/3. Now, a 1/3 power would be the same thing as a cube root. A 2/3 power is going to be a cube root squared. So this is a type of question that you should be able to evaluate without a calculator. You do the cube root and get 4, and then you square the 4 and get 16. Now, if you do happen to put this into your calculator, you need to make sure that you put that in a parenthesis. Otherwise, it'll take 64 squared, get an answer, and then divide by 3, which is not the same thing whatsoever. Okay, so let's look at the graph of y equals 2 to the x, and then we've got information to fill in there as well. So what I'm going to do is I'm going to make a table of values here. Now, I can get these tables of values by hand, but we can get them on the calculator as well. I'm going to go ahead and just type some numbers, write some numbers down, and then we'll go and look at what it looks like on the calculator. Okay. Now, I can get all those numbers again by hand by just putting those powers in. 2 to the negative 2 power would be the same thing as 1 over 2 squared, which is a 4th, or 0.25, and the same thing the rest of the way down there. Going to the calculator here. Okay, so we're going to go to our y equals. And I'm going to do 2 to the x power. Now, I've been doing other things with my calculator here, so I'm going to need to change my window. Anytime you need to change your window back to normal, sorry, just waiting for the bell there. We're going to go to standard number 6, and that is something that you need to be able to do because you're changing your window a lot in this class. Okay, so that's what we end up with there, which I expected because my b value is greater than 1. And to get my numbers there that I'm going to plot, okay, here's what I had in my table over there. I didn't write all those down. I just wrote enough to get a good idea of what this graph looks like. And then now we're going to put it on paper. So over here, we've got negative 2 barely above the x-axis, negative 1 just a little bit more above, 0, 1, 1, 2, 2, 4, and 3, 8. Yeah, so make sure that that was 8. Now, you might be inclined to change the window or to change the scale of your graph to not go by 1 because of how small those numbers are on the left, but the numbers get big fast, so it's really better to not do that. Now, try to make it not look like you're touching the x-axis. Mine's super close. It might actually be. We do have an asymptote. Now, you don't necessarily need to put the asymptote in here, but it would be along the axis here. I'm going to do it just so that you know it's there. Okay, that's the x-axis, which is the same thing as y equals 0. My intercepts, we're intersecting the x-axis here at or the y-axis at 0, 1. My domain is all reals, or negative infinity to infinity. My range, I have nothing negative, and again, I'm super close to 0, but I'm not really there, to infinity. And then this graph would be increasing. Now, we can take these graphs and shift them the way that we did with other graphs. We can move them left and right. We can move them up and down. We can stretch them and squish them and all that fun stuff. So, for example, same graph, but this time we've got a plus 3. That plus 3 is going to move the graph up 3. So, we could just take all those same x values that we had before and take all the y values that we got and just add 3 to them. So, I had 0.25, now I have 3.25. I had 0.5, now 3.5. I had 1, now I have 4. I had 2, now I have 5. I had 4, now I have 7. So we can plot those points. We don't even have to look at the calculator, but we will in a minute. Negative 2, up 1, 2, 3, a little bit more than 3. Then we're going to be a little bit more than that. Then 0, 4. Then 1, 5. Then 2, 7. Okay. Now, whether it's obvious or not, in this case, what happened is your asymptote moved up 3 as well. So this is the line that I'm getting super close to but not touching. Okay, so that's going to be y equals 3. My intercepts, that's going to be over 0, up 4. The range in this case, well, we'll skip that one. The domain is still going to be all reals. And again, you can write it with the infinities if you want to. The range, my lowest y value is really close to 3, but I'm not touching 3 because of my asymptote, and then we're still going to infinity. That graph would still be increasing. Okay. Now just to see what that would look like in the calculator, we're going to go to our y equals, and all we have to do is just stick a plus 3 on the outside here. Make sure you don't put it up in the exponent. Okay, and then graph. And again, literally the graph just moved up 3. And there we are. Now, it does not show that asymptote line. Again, you have to know that that's there. All right, so this graph, we've got a b value this time that's 1/2, which means this graph is decreasing. Now, you'll see that when we graph it here in a minute, but the value that's right here is less than 1, so that's why it's decreasing. Now, the 3 that's in the front is going to stretch it vertically, but the thing is, with these graphs, you really can't tell that they're stretched. It would be like steeper than if you hadn't done it, but otherwise it's going to be hard to tell. Now, again, I'm going to go ahead and write some values down here, and you'll see them in the graph here in a minute. So this first one doesn't fit on the graph, but I'm still writing it down just to give me an idea of what's happening. Okay, so let's look at the graph here. So we've got y equals 3, 1/2 to the x power. Always double check, make sure you typed it in there correctly. Okay, so we graph here. Okay, so that graph is decreasing because we're going from left to right, we're going down. Okay, look at the table. Okay, and you can see the values that I picked there. I was looking for numbers that were whole numbers, if at all possible, numbers that weren't too big, numbers that weren't too small. So I stopped at 3 because that's already pretty small there. So putting it on paper then, negative 212, I'm just going to kind of estimate that that's going to be up there. Negative 1, 6, 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 1, 1.5, 2, a little bit less than 1, and 3 is, getting pretty close to 0 there. Now this graph didn't shift up or down at all, so my asymptote is still going to be the x-axis. So we're going to kind of just level off there at the end. Okay, so this is going to be my domain. My range is just like my first graph there because we're not shifting anything, and we're also not flipping anything. If you flip vertically, you're going to change your range of 0 to infinity to be negative infinity to 0. Instead of having all positive numbers, you'll have all negative numbers. Asymptote is y equals 0 or the x-axis, and my intercept here would be 0, 3. All right. So the last part here is about doing the modeling, but also solving exponential equations. So you can solve them graphically, which we've talked about before. You could put this as one of your y sub 1s, and this is your other y sub 2, and look for the intersection. In this case, they intersected about 3.32. Oh, sorry. I changed this problem. I forgot. It should be 3.46. Sorry. Now, using logarithms, okay, I'm going to get this exponential expression by itself. So we're going to add 1 to both sides. And then I'm going to take the log of both sides. Now, if you remember doing this from Algebra 2 or from Pre-Cal, there's 2 different logs. There's the log log and there's the ln log, the natural log. It doesn't matter which one you use because in the context of this question, they're going to work exactly the same. So I'm going to take the log of both sides. So when I do that, I then have a property that says, hey, when you have an exponent, you can pull that exponent down in front, which gives me this. Now, the log of 2 and the log of 11, those are just really bad decimals. So I can divide both sides by the log of 2 to get the x by itself. Now, one thing to be careful about when you do that, make sure you close those parentheses in your calculator, otherwise you'll get the wrong answer. You're going to take the decimal for the log of 11, you're going to divide it by the decimal for the log of 2, and that's going to give you 3.46. Now, if you put that in your calculator and check it, you're going to take 2 to the 3.46 power. It gives you 11.00433455. That's because it's rounded. Okay, so it's going to be close, but not exact. Now, I don't know if they're going to expect you to do this on the exam or not, but it was in your book, so I did want to show you how to do that. And you do have some to practice in your homework. All right, so here is the modeling stuff. Okay, and we will talk a little bit about solving with graphing here in a minute, too. So we have a radioactive element that decays in a way such that the present amount each year is 0.95 of the amount present the previous year. So that 0.95, that'd be the same thing as 95%. At the start of 1990, there were 50 milligrams of the element present. Produce a table of values showing how much of the element is present at the start of each year from 1990 to 1998. So they haven't asked me to write an equation yet, but you do need to think about that to figure out how you're going to do this. So we're going to make a table here. This is going to be our year and our amount. So in 1990, we have 50 milligrams. Okay. Now, to find out my next amount, I'm going to multiply times that 0.95. Be careful the way it's worded. If it says it decays this much, you need to think about, well, how much am I actually going to have? In this case, I actually have, because it says present, I actually have 95%. So I'm going to take 50 times 0.95. That's going to give me 47.5. And again, that's going to be 50 times 0.95. Now I'm going to take that answer times 0.95. And then once I go from there, this one's exact. I'm just going to keep going. But then from there, I've got horrible decimals. So what I'm going to do is I'm just going to round everything off to 1 decimal place, just because when we go to graph this, it's going to be an estimate anyways. So that's going to be 40.7, 38.7, 36.8, 44.9, and 33.2. And again, just every time multiplying my previous answer times 0.95. Okay, part B, the rule for this situation, which means the equation, is n equals k times a to the t power, where n milligrams is the amount of element present t years after the start of 1990. Find the value of a and k. All right, well, in this case, my n is going to be, okay, k is what I start off with to begin with. That's going to be 50. I'm multiplying by 0.95 each time, and then that's to the t power. Now, practice that, okay? So it says that t is the years after 1990. So in 1990, I am 0 years after 1990. When I plug 0 in, do I get 50? Yes. 1990 is 1 year after the start of 1990. If I plug 1 in, do I get 47.5? Yes. So we're good. Okay. Now sketch the graph, and then how long will it be before there is 25 milligrams of this element? So when I sketch this graph, I want to make sure that I have 25 on here. The picture that I have here is really too small. I don't want to go by ones. That's a ton of numbers to put on here. You know, going by twos maybe would be nice, just with how close my numbers are. But I don't have room to even do that. So what I'm going to do, first of all, is I'm going to do a little zigzag here. And that's going to show me that I am actually not starting at 0. I'm going to jump up, and I'm going to start here at 20. And then I'm going to go by twos from there, but I'm only going to write every other number just because otherwise it's going to get too cluttered. Okay, and then I'm just going to stop there. All right, and then on the x-axis, I'm going to go by ones, but I'm going to, again, just write every other number. I don't know what this side's going to need to be because that's the part D that we're going to do. Okay, so as far as my sketch, I'm going to do the best that I can here. At 0, I'm at 50. At 1, I'm at 47.5. And remember, we're going by twos, okay? So 47.5 is going to be super close to 80. 45-ish. Okay, is going to be here in between 44 and 46. Oh, we're over one too far. And 42.8 is about 43. And about 41. About 39. About 37. About 45. Oh, wait, that's not right. How about we write 34 over here? Sorry if you've been staring at that thinking, why doesn't she fix that? 35. And then about 33. Okay, so we're trying to find out when is there going to be 25. So 25 would be right here. So if we kind of continue this down, I'm going to say that 12 is a good guess. Now we're going to plug this in and see here. So you can actually do this one using the method we talked about earlier. You can do 25 equals 50.95 to the t power. So what you would do is you divide both sides by 50. So you get 1/2 is 0.95 to the t. You would take the log of both sides. And then that t is going to come down. And then you would divide both sides by the log of 0.95. Or we graph it. You graph this part in your calculator, you graph this part. Or if you'd rather, you graph this part and you graph this part, either way. Okay, let me just show you a reminder of what that looks like. Okay, so my y equals here. Let's just go ahead and do the way the graph looks on my picture there. So let's do the 50.95 to the t power, or in this case to the x power, and then we want it to be 25. Now for my window, make it be what it is on your paper. So we're going from 0 to 20. by ones. On my y scale, in this case, if you want to, you can go ahead and start at 0, because I got plenty of space on the graphing calculator. We're going to 52, and we're going by 2s. So here's my curve for the element. And then there's my other one. So we're going to see where they intersect here. We're going to hit second in the calculate button, go to number 5. We hit enter, enter, enter. Remember, our estimate was 12 years. It's 13.5 years. So not bad. And that's the same thing you would get if you solve this equation up here too. All right, so the last part, we have $500 deposited into a bank account that pays 5.4% interest per annum, which means per year. How much money would there be in the account at the end of 6 years if the interest is compounded annually? How long before it's doubled? And then actually show the graph. Okay, so we have this formula that we've already used in here. So that's going to be my present value is $500. 1 plus 5.4 over 100 to the 6th power. Well, that's really actually 500 1.054 to the 6th power. And that gives me $685.51. Now, this minus the 6 is the equation that we're going to use to figure out part B. How long is it going to be before the account is doubled? So we have 1,000 for my future value, 500 for my present value. This is going to be my rate, and I'm looking for T, or I'm looking for X. So we can solve that using the logs, like I showed you in the last one, or we can graph this one. I'm going to kind of skip past this part here and just tell you that T is 13.2. Okay, so again, you graph the 500, graph the right-hand side, graph the left-hand side, and you'll get 13.2 there. Now, as far as the graph, actually, we're going to have to do that part anyways, so let's go ahead and stick this in here, and then I can show you how we get that 13.2. So we go to our y equals. This is going to be 500, 1.054 to the x power. Now, as far as our window on this, we're looking for where it's doubling eventually. So let's go ahead and make a window. I'm going to just keep 0 to 20. I think that's probably good. In this case, let's start with 500 because that's how much money we started off with. Oops, wrong place. Let's start with 500 here. And then let's start with 1,000 here. And let's go by 25s. Now the 1,000 is at the very, very top there. If you actually did want to solve this part using the calculator, what you would actually need to do is not make it go to 1,000. Let's make it go to, I don't know, 1,500 maybe. Because I need to have some space to be able to see where 1,000 is. And then we'll put in the 1,000. And there we go. So again, if we do our intersection, that's going to give me the graph there. Now I'm going to get rid of the 1,000 here just so we can see some points. Okay, so what I'm going to do is I'm going to plot just some nice values. So I'm going to plot, of course, oops. A little bit more. Okay, there we go. So I'm looking for some nice numbers. So of course I'm going to do 0, or that's X and Y. I'm going to do 0, 500. 1, we'll do 1. We'll do that one. Now, my scale is going by 25s here, so I'm looking for numbers that are multiples of 25 or close to that. 4, no, let's not do 4. Let's do 5, so that's 650. Okay, we're done. We can stop moving now. Okay, 5, we had 650. 7 is 722. And 9 is 800. And 11 is pretty close to 1,000. All right, so now let's make this bigger here. All right, so on my graph here, I'm going by ones at the bottom again. And then I'm starting at 500 here. Now on the last graph, I kind of did a zigzag. I don't have room for a zigzag on this one, so I'm just going to leave it. I'm going by 25s, but I'm only going to do every other one. So 550, 600. And 1,000 up there at the top. So we've got a point here. 1 is about 525. 2 is about 550. Then I skipped a 5. 5 is 650. 7 is about 725. 9 is 800. And 11-ish. Is about 1,000. It was a little bit shy of 1,000. So here, a little curvy there at the end. So that's my graph. All right.